Okay, so we've been talking about chapter two. We talked about, again, sort of significant figures last time. We also talked about scientific notation. We started getting into, at the end there, really dimensional analysis, which relates to conversion factors, equalities, and really the way you're supposed to sort of show a lot of the work in chemistry is to do dimensional analysis. And as we see here on sort of the screen, dimensional analysis really is a way in which we use conversion factors to go really from one unit to the next. So, for example, I think what we were talking about last time was that, let's just say we had this guy here, which is considered an equality. And an equality is, as we will see and talk about more today, is basically two things that are on different units but do represent really the same amount of something. And from any sort of equality, we really could write two different conversion factors. And conversion factors are these guys here, although I did scratch one out, I think, last time. But they're really just fractions where we put one unit up on top, one on the bottom, and then we obviously could reverse it. For example, here, unit B could go up on top and unit A could go on the bottom. So that when we sort of set up our calculation here, this is what's sort of considered dimensional analysis. And what we want to do is basically cancel out the units we're not interested in and keep the units that we are interested in. And really the simplest way to achieve that is opposites. So opposites pretty much will cancel out units. So for example, here we started with unit A up on top. The opposite location is to have unit A on the bottom, and they will cancel each other out. And that's because everything that's pretty much located across the top, all these guys will be multiplied. And everything that's sort of on the bottom, if you will, all these guys will then be divided. You'll divide the top by them. So what we're essentially doing when we go in opposite locations is if I put unit A up on top and unit A basically is on the bottom, when you divide those things, they equal 1 or essentially cancel out. Is the same idea if you took 2 divided by 2, that would equal 1. They would cancel each other out. Same thing as well, if you had a unit that was on the bottom, to get rid of it, you would want the same unit up on top. So that's a good thing to keep in mind when you sort of do this dimensional analysis. You want to kind of do opposites will cancel out our units. Any questions on that stuff there? Okay, then let us continue talking about sort of these conversion factors and equalities. So as I mentioned before, equalities really are two sets of values that are on different unit scales, but they really do represent really the same quantity of our value. So like, again, if you had 100 pennies, that's the same amount of money if you had $1. They both basically represent the same amount of money. Here we have 1 meter is 1,000 millimeters. That's an equality. Again, they represent the same amount. 1 pound is 16 ounces. They represent really the same mass there for each of those things. 2.2 pounds is a kilogram, same idea again. And from really any equality, we could write two conversion factors. So here, for example, if we took this one, we could say that 1 meter is up on top, 1,000 millimeters are on the bottom, or you could reverse it and you could write a second conversion factor where 1,000 millimeters are on top and 1 meter is on the bottom. And again, you really won't use both of them in a calculation. You'll use whichever one you need. So for example, here again, if we were starting with, let's just say 32 millimeters, and we want to know how many meters that is. So if we want to know how many meters that is, we, again, even though it's not really written as a fraction, you can kind of think of it as a fraction. This is basically over 1. And really what that means is the millimeters are the units we want to get rid of, which, as we just talked about, means opposite. So that means we would want to use the conversion factor here on the left and do our dimensional analysis, where we would put 1 meter up on top and 1,000 millimeters on the bottom. And again, here, math-wise, what we're doing is everything on top will be multiplied. So we're going to multiply basically 32 times 1, which will give us 32. We're then going to come through and divide by everything on the bottom. So on the bottom here, if I can find my thing, there it is. We're going to divide by 1, and then we're going to divide by 1,000. So barely just divide by 1,000, and we will end up with 0.032 millimeters. Now, in terms of significant figures on our answer, anything that's an equality for our purposes here in lecture, you could consider an exact number, which means we're going to really ignore the significant figures in that sort of equality or conversion factor, which means we would want to go back to our original number here, which is 2 significant figures. That's not a 2. Let's try that again. The 2 significant figures. And that means that our answer here should end up with 2 significant figures as we are multiplying and dividing in terms of our calculation that we're doing. Now, I think I might have mentioned last time, but let me just clarify one more time in terms of this idea here. We talked about the idea that there's 2 different types of units. There's the US units, and there's also the sort of metric units, if you will. And technically speaking, if you did a sort of metric to metric conversion, like what we just did there, 1 meter is 1,000 millimeters, or an English to English conversion, like pounds to ounces, those are considered exact numbers. If we do cross over and do sort of like a English to metric sort of conversion, like 453.6 grams is a pound or something like that. Technically speaking, you should look at the significant figures in those conversion factors. And that's really the truthful sort of answer. But for our purposes here in this class, we're just going to keep it really simple. If anything is sort of a equality, like any of these guys here, even if it is sort of metric to English equality and you use a conversion factor, for lecture part, you could safely assume that it is an exact number and sort of ignore it. Any questions?
Professor, I have a quick question.
Yes, sir.
Maybe I don't know if I should ask it here or in the session following up, but can you show us how to convert from grams of metric to the American standard, like to pounds?
Yeah, so I tell you what, if I don't answer it here in the lecture, I'll be happy to do a discussion.
Okay, all right.
We're actually going to be doing some conversions that I don't know if we'll cover that exact conversion, but we're going to be doing some conversion examples here in just a bit. So,
okay, thank you.
Yeah, but if not, just definitely ask me again in discussion. We'll be happy to kind of go over that one for you. All right, so equalities, obviously, we see in a lot of places like on labels, right? For example, here, 5 ounces is represented basically the same as 142 grams. So that's an equality. Equalities and significant figures. So as I mentioned before, because they're basically considered exact numbers, we do ignore them in terms of how many significant figures our answer should have. So I would say probably a pretty safe rule of thumb is if you're just strictly doing a conversion, like actually the question that was just asked, I'm getting old, I don't remember what it was, but like say pounds to grams, for example. If we're just simply converting a number, let's just say we started with 5.0 pounds and we wanted to go to grams, what we will end up with in terms of significant figures is usually pretty safe to assume is the amount of significant figures in that original number probably will be the correct number of significant figures in your answer, because everything in between will essentially be a conversion factor. So for example, if we were to do this one equality that we would use is 453.6 grams is 1 pound, for example. Some people round this to 454. I personally use this number because it was beat in my head, so I can't forget it. We will use this as, again, a conversion factor, which means basically we could write 453.6 grams over 1 pound. Our 1 pound is 453.6 grams. So again, we would start with this number here, and that would be 5 pounds. Again, not written as a fraction, but if you want to think about it in terms of top and bottom, our pounds are up on top, which means to cancel it, we need the pounds in the opposite location, which would be this conversion here. And we would put 453.6 grams over 1 pound. Again, here, what we're essentially doing is just multiplying the top here. So that would be 5 times my 453.6. And then technically we'd be dividing by the bottom, but all the bottom is basically 1. So you can, but you don't necessarily need to. On my calculator, I'll end up with 2268 grams, for example. Now, where I'm going to think about in terms of equalities and significant figures is this is going to be a definition or an exact number, which means I'm not going to worry about it, which means, as I've been saying, I could pretty much default back to this number here. And I see it has basically 2 significant figures, which means I really should take this guy to 2 significant figures, which means this would round to 2,300 grams. No decimal point written there. Or again, you could do something like scientific notation to the 3 grams here. So 9 times out of 10, maybe even more than that, if you're just simply doing a conversion problem where there's just conversion, maybe even multiple conversions after conversions, probably almost a safe bet to go with the same sig figs as the original number. And I would say probably, again, nothing's 100%, but in probably more cases than not, you probably will hit the sort of correct number of significant figures that you're looking for. So here again are some other equalities and stuff like that. And again, from any of those things, we can write some conversion factors. Now, this is what I was saying a second ago. Here we do have equalities and significant figures, and this is really the right way to do it when we are going from a US unit to a metric unit. You do count the significant figures. So as you can see here, basically this would kind of count towards the significant figures 3. This would be 3, and this would be 3. Again, this is sort of a metric to US conversion, and you should look at the significant figures. With that being said, again, like I said before, we will, for the most part, consider it an exact number, even if it is a conversion like this. And I will say probably in most cases, even if you did count the sig figs on these guys, still usually that first number is probably the lower number of significant figures. So, you know, you won't have to worry too much about it. So the right way is really what it says on the screen, that, you know, you should take into account the number of significant figures when you're doing metric to an English conversion. The only one you don't really have to worry about is actually this conversion here. And this is one that you should know. 1 inch is exactly, and that's why people usually emphasize exactly 2.54 centimeters. So even though that again is sort of an English to metric conversion, we still consider that an exact number and would not count it. So the right way, metric and US, should look at the significant figures when you're doing the calculations. I'm going to say for just lecture, and again for lab, if they tell you something different, it is correct to do it this way. But definitely for lecture here, you know, even if it is that metric to US, you could still think of it as an exact number. And in probably most cases, you will still really be probably okay. Again, in terms of conversion factors, any equality can really be written as 2 conversion factors. And again, like I said, you will not use both of them. Otherwise, you'll cancel each other out. So for example, here, 1 hour is equal to 60 minutes. You can put 60 minutes on top or 1 hour on the bottom, and vice versa here. And again, it's a really good way to do calculations using dimensional analysis, showing all the units, because a lot of times people don't understand maybe what they should be doing sort of in terms of the math part of it. So if you really sort of keep things written out in dimensional analysis as you're doing these calculations, where you can see the different units and one's on top, one's on the bottom, it should hopefully help you understand that, you know, you should maybe be dividing, you should maybe be multiplying in certain situations. So keeping everything sort of separate really does help out. Here are some very common sort of conversions. These are some metric to metric conversions. And again, here, technically speaking, these would all be considered exact numbers. This is US to US sort of conversions, which also would be considered exact numbers. This is where we cross over. And as I mentioned a second ago, the correct answer is you should look at the significant figures here, and it would be the significant figures where the number is. But for lecture, you don't have to worry about it. We'll sort of consider them exact numbers, even though one that's not 100% correct. The only one that usually is considered an exact number in that crossover is that guy right there. So I would say if you're doing some type of problem, maybe the Mastering Chemistry, and you do come across one of these, you should think about the significant figures when you're doing it, because obviously it's probably programmed that way. But again, for lecture, you could think of those guys as exact numbers and not have to worry about it. Any questions on that?
I have a question.
Yeah.
In the test, will we be using the significant figures or the exact numbers?
For the test, you should always give your answers to the correct number of significant figures. We talked about some calculations of multiplying, dividing, and adding and subtracting. In terms of these guys here, the idea with exact numbers are they're basically these definitions here, and they basically could have an unlimited number of significant figures. So when we're doing a calculation like a conversion factor where, we're doing a bunch of these sort of conversions here that come from these equalities, maybe you're doing a bunch of them, we basically ignore the contribution of these conversion factors to the answer in terms of the significant figures. And again, in most cases, you could simply just go back to the original number, and that will give you the right number of significant figures for your answer. The only one, technically speaking, that you shouldn't do that with is these, but for lecture, you can do it with that and consider those exact numbers, and you ignore them. Again, you do want to be careful, though, again, on the Mastery Chemistry. If you come across it, you should take them into account. But like I said before, even taking them into account in probably a lot of examples are problems that you do, your Sig Figs that you started with is probably the right number Sig Figs to end the calculation with. Other questions on that? Now,
I'm sorry, I have another question. So do we have to memorize these in the metric system and the US system for the test, or are we going to be provided with like the conversion?
So you'll be provided with some of these. There's a review sheet, and on the review sheet, it'll say, for example, you should know this conversion here, which means it would probably not be provided for you. So I would say most of them will probably be provided for you. Again, though, if you look at the review sheet and it says specifically like, hey, you should know this one, it would obviously not be provided for you, but probably most of it will be provided. Other questions? So again, just looking at some of these things that we talked about here in terms of writing conversion factors. You're welcome. From any of those guys, 2 conversion factors. So 1 meter is 100 centimeters. We will do our 2 conversion factors, basically our fractions. And here again, we'll look at our 2 conversion factors. So looking at, a problem, for example, if you weighed 175 pounds and you wanted to know how many kilograms that is, again, we would start with the number that was given to us, which is 175 pounds. And here we would want to choose the correct conversion factor. Again, this is technically pounds up on top, which means we do want pounds on the bottom. So we would want to use this particular conversion factor here, 1 kilogram up on top, 2.2 pounds on the bottom. Now, we will divide out pounds by pounds, so those units cancel. The only unit left here is kilograms, which are on top. We are going to basically multiply everything on top, which is 175 times 1, and divide it by the number on the bottom, which is 2.2. On my calculator here, I could find my ink. There it is. We end up with 79.545454 and so forth. And the units would be kilograms. Now let's talk about the Sig Figs and sort of what I was saying a second ago. Now, technically speaking, we are crossing over here and we should look at the Sig Figs here. That's 3 Sig Figs, but we do see here that my number is also 3 Sig Figs that we started with, which no matter which one you look at in this case, 3 is the smallest, and we actually would end up 79.5 kilograms as our answer. So even though we did take this into account, as I mentioned before, usually that first number is either equal to that conversion factor in terms of significant figures or less significant figures in a lot of cases. Again, nothing is 100%. So that's why I was saying earlier, in most cases, if you just kind of go with that first original number that you had there, you probably will end up with the correct number of significant figures. So let's look at some of these guys here. We want to write some equalities and 2 conversion factors for liters and milliliters. So there are, 1 liter is 1,000 milliliters. This is what is referred to as an equality. And again, from this equality, these are the 2 conversion factors that we could get. And again, 1,000 milliliters over a liter or 1 liter over 100 milliliters. Here is a conversion between, or an equality between inches and meters. There's 39.4 inches in a meter. Again, that's an equality. Both of those things represent the same amount of distance. We could write 39.4 inches over 1 meter, or again, 1 meter over 39.4 inches. And here, 1 milligram, I can say that wrong, 1 milligram is equal to 1,000. That should be micrograms. Sometimes they use this abbreviation, the little U-ish. And again, that's an equality. And again, our 2 conversion factors that could come from it. Any questions on equalities there and kind of conversion factors, writing them? Now, sometimes you are given an actual conversion factor that may be specific to a problem. So for example, if your car is traveling 85 kilometers per hour, that may be given in the problem. And we can also use this as a conversion factor. And basically what that means is, as it says here, you basically are going 85 kilometers in 1 hour. It's like the same thing if you're driving 65 miles per hour, it means you drove 65 miles in 1 hour. And from these equalities, you can write, again, 2 conversion factors. And we would consider in this case the significant figures here on these conversion factors, because really it's not a sort of true conversion in the sense, is not necessarily one that always happens that way. If you want to think about that in that sense, you're not always perhaps driving 85 kilometers per hour. Maybe you're doing 65 kilometers per hour. It's not something that always is the same. For example, like there's 60 seconds in a minute, right? No matter how you squash it or do it, every 60 seconds is a minute. And that's always what it is. Again, if you're driving, obviously you're not always traveling the exact same one. But we oftentimes are given conversion factors. And this brings up, sort of a good point as well, that, sometimes you do have conversions where you may need to kind of convert 2 different units. So for example, let's say we were doing 55 feet per minute, right? I think we're going to see a problem later on where maybe you're walking, say 55 feet per minute. And maybe you want to figure out, how many miles per hour that is. So sometimes people get really confused when they try to do a problem like this. And the idea here is where dimensional analysis can really help you out is to keep the units separated. So if you just think of these as really two different problems, the first thing you need to do is take feet to miles, and you need to do that you end up with miles up on top. The second thing that you need to do is convert the minutes to hours, and you need to make sure that the hours basically stay on the bottom there. So if we were going to do a conversion like this, we would want some equalities. So for example, there's 5,280 feet in 1 mile. And from that conversion, our equality, we could write two conversion factors, 5,280 feet over a mile, or a mile is 5,280 feet. So if I were to do this sort of conversion here, I would start with my units. And again, when I write it, it's really important to sort of separate out the two units. So usually the number stays with the first unit, and usually on the bottom, it's like 1 of the second unit. So really what this is 55 feet per 1 minute. That's basically what we're starting with. So we're going to use dimensional analysis, and we think about our feet we want to get rid of. So feet are on top, which means we really need to use the conversion factor where feet are on the bottom, and that would be 5,280 feet in 1 mile. If I stop the conversion right here, or the problem right here, feet divided by feet would cancel out. And the units I would be in at this particular point, just the units, would be miles on top and minutes on the bottom. So I have successfully changed the top unit into the unit I want. I now need to do the bottom unit. So the bottom unit does need to go from minutes to hours. And we know that there are 60 minutes, right, in 1 hour. That gives us two conversion factors. 60 minutes over 1 hour, or 1 hour over 60 minutes. Now, why it's important to set this up in dimensional analysis, when we look over here, you should hopefully be able to clearly see that the units of minutes are on the bottom. And that's important because I know that to get rid of the units of minutes on the bottom, I need the units of minutes in the opposite location, which means I actually need it on top. And that would be the next part of the conversion problem here. On top would go 60 minutes. On the bottom would go 1 hour. I am now essentially dividing minutes on top divided by minutes on the bottom, and they actually cancel. Now, if I look at my units, up on top is miles, on the bottom is hours. I have now successfully converted my units to miles per hour. Now, math-wise, what we would do is we would multiply here and multiply here. And I'm going to give you a very good hint that when you're doing multiple sort of calculations together or conversions together like this, you can multiply as many numbers as you like up on top. So I would take 55 times 1 times 60. When you get to the end of the top, it's important to hit enter. And then this is sometimes where people screw up these calculations. In this particular case, we really only have one number, but if you had multiple numbers on the bottom, people like to put it into their calculator all at once. And if you don't do it correctly, you will get the wrong answer. So my recommendation is multiply as many numbers as you like across the top, hit equals, and then individually divide it by all the numbers on the bottom. So for example, here we would divide it by 1, hit equals, divided by 5,280, hit equals, divided by 1, hit equals. You don't really need to do the ones, but if you like to, you can. And if you do all that, we will end up with 0.625 units are miles, which is what stays with the number, per hour. So we're obviously not traveling super fast here because maybe we're walking, but it's really important. And you can see here, by doing these problems in dimensional analysis, you can really keep track of where the units are, because it is very common when people do these type of problems that they sometimes will do what I sometimes refer to as like the kind of stacking method, where they write something like, okay, I'm taking 55 feet per minute. I'm dividing it by 5280 feet per mile. And they have no idea what they're multiplying, what they're dividing, because everything just starts stacking. And you usually end up multiplying where you should be dividing, or dividing where you should be multiplying. And again, if you clearly do everything here in dimensional analysis, where you could clearly see this unit's on top, this one's on the bottom, it should make it really easy to sort of do these conversion type problems. Any questions on that? Here's another sort of conversion factor that you could draw from a problem. In this particular one, a tablet contains 500 milligrams of vitamin C. And again, basically the equality would be one tablet, 500 milligrams. 500 milligrams is a measured value, and it has one significant figure. And we would technically sort of take those into account. So I know I said as we go from English to metric, we'll think of those as exact numbers. The one thing where we will still consider the significant figures in a conversion factor is one that's sort of derived from sort of a problem such as this. So here we would want to look at the 500 milligrams, and it does have obviously one significant figure. Another very common thing that we get sort of in problems sometimes are percentages. And again, a very good way to convert a percentage into sort of a usable number or a usable conversion factor is to assume like 100 of something. So for example, if you got 85 on your exam, that probably means that you got 85 points out of 100. And that makes just really the numbers easy. So here it says we have 18% body fat by mass. What that means is I would have 18 kilograms and 100 kilograms of body mass. Could also do it in pounds if you wanted to, 18 pounds of body fat and 100 pounds of body mass. So, I mean, you could do any type of conversion like that. Same idea, 18 pounds of fat and 100 pounds of mass or body mass. You obviously could write your two conversion factors. In reality, you really could assume any number you want, but again, we usually assume 100 because it keeps the numbers the same. Obviously, if you assume 200, then you would obviously have some different numbers. Here's another example, again, a common one, obviously, in terms of medication. One capsule has 250 milligrams of Keflex, which is obviously an antibiotic here. And again, we can use this as conversion factors here because it comes from the problem. We would look at this number here. The way it's written has only two significant figures, the 2 and the 5, the 0 not being significant here as there is no decimal point written. So let's take a look at a couple of these here. Let's again sort of talk about where everything comes from. We have meters to decimeters. So our equality is here. 1 meter is 10 decimeters. And again, our two conversion factors that we could write. Here's 18% gold. So here we're assuming 100. So if we assume we had 100 grams of jewelry, 18 grams of it would be gold or be made up of gold. And again, that would be our equality for which we could then write our two conversion factors. Again, we would only be using one. And 1 gallon of gas is $2.40. Clearly, this book was written a long time ago. Probably was expensive when they wrote it. But again, basically what that means is you could get a gallon of gas for $2.40. And $2.40 over 1 gallon, or 1 gallon is $240, maybe soon, but $2.40 per gallon. And again, you know, obviously if you filled up your gas tank and you could put 14 gallons in your gas tank and you want to know how much that's going to cost you in dollars, you could use something like that in terms of a conversion factor. Here we would start with our 14 gallons that we pumped into our car. We want to get rid of gallons, so we will use the conversion factor here on the left. Gallons on top, gallons go on the bottom, $2.40. And you could fill up your car for a very reasonable in today's day and age of $33.60, I guess. $33.60. Technically speaking, in terms of Sig Figs, this guy, we would probably look at it since it's a specific sort of conversion that has 3 significant figures, but my original number here only has 2, which means technically speaking, we probably would round that up to $34. We would not put the 0.00 because now it would have 4 significant figures, right? So we would just leave it at 34. Any questions on that there? All right, so we sort of talked a little bit about this as we've been talking, but again, using these conversion factors in problem solving, that again is what is commonly referred to as dimensional analysis. And again, that's really just a fancy way of saying we're going to use conversion factors to cancel out units we don't want to really get to units that we do want. So let's take a look at some of these things. There's certain steps when you're doing these type of problems, which, can be very helpful for you. Sometimes it's really important to write what's given to you in the problem. You also might want to write what you're trying to find. You then want to kind of think about what equalities are important and obviously the appropriate conversion factors. And really, the 2 main things here is you need to set it up using dimensional analysis, showing those units canceling, and then obviously reporting your answer to the correct number of significant figures. Now, what do you need to show, to get sort of full credit on an exam or quiz? Really, you just need to show the setup with the dimensional analysis and the units, and the final answer to the correct number of significant figures. If it helps you to write what was given to you in the problem, if it helps you to write what was found in the problem, if it helps you to write out all the equalities and all the conversion factors, you can definitely do that. You don't necessarily have to do that on a conversion problem. You do need to obviously show sort of the setup like I just did over here, clearly in the dimensional analysis way where we have the conversion factor and then obviously all the units and the correct number of significant figures when it's all said and done. So if we look at one here, if a person weighs 178 pounds, what is the body mass in kilograms? So obviously here we would want a conversion between pounds and kilograms. So we would want to look it up probably in the table. And we saw earlier there's 2.2 kilograms there in a pound. So I'm sorry, that's that backwards. 2.2 pounds in a kilogram. We would look up our equality here. We would get our 2 conversion factors from it. And again, we're going to be starting with our number that was given to us, which is pounds. So pounds again are on top. So we want to use it where pounds are on the bottom. So that's why we would use the conversion factor on the right there. The pounds do cancel. We're going to multiply 178 times 1 and divide it by 2.20. So again, if you're punching this into your calculator, you don't necessarily have to multiply it by the 1, but you would take 178 times 1 and hit equals, divided by 2.2. Again, here you can see sort of what I was saying earlier. Even though technically this is a English to metric conversion, it does have 3 sig figs, which is what we should look at. But we also again see 3 significant figures on our original number. And that's why we should end up with, which is 3 significant figures. So as I mentioned earlier, in most cases, straight conversion problem, probably that original number is the correct number of significant figures you should give your answer to. Again, not 100% of the time, but probably fairly close to 100% of the time. But again, you should, and again, sometimes people will look at these guys here in terms of it being that metric to English sort of conversion. Also a reminder that your calculator does not always spit out to you the answer, obviously, in the correct number of significant figures. So for example, on your calculator here, you get 80.909090 and so forth. You do need to take obviously the initiative there and round. We round to the 9 because the next number there is 0. So we would just drop the rest of the numbers and that gives us our answer. So here we have a rattlesnake is 2.44 meters. We want to know how many centimeters is the snake. So again, we want to have some type of conversion between meters and centimeters. There's 100 centimeters in a meter, and we could use that as a conversion factor. And our inequality to get our two conversion factors. Again, here we're going to start with the number that was given to us. We again will see it is basically up on top meters, which means we do need meters to be on the bottom to properly cancel out, which is why they chose the conversion factor there on the left. Here we're going to take 244 times 100 and divide it by 1 gives us 244. This is a metric to metric conversion, which means this is considered an exact number, which means you do not need to worry about it in terms of how many significant figures your answer should have. That means that pretty much we're left with just this number, which again is our original number, as you might be seeing a pattern here. And that had 3 significant figures. We end up with 244 there, which is 3 significant figures as well. Any questions on that one there? So again, in terms of what you need to show, on a test or something like that, to get full credit, it's really this last part here. Again, everything's sort of set up. I personally do the little parentheses around them, but again, something like that where you see the units, you obviously give the answers the correct number of significant figures. Now, when we are using 2 or more conversion factors, a couple of ways that you can do these problems. You could absolutely do these problems like I sort of did an earlier example when we were doing like the feet per minute to miles per hour. You could do it all in one big calculation. You could also do it in sort of step by step. So kind of do one conversion, get an answer, take that number, do the next conversion, get an answer, do that number, take the next conversion, and get an answer. If you do decide to do it sort of in the step-by-step approach, it's really a good idea, as we might have talked about before, to avoid extreme rounding until the very end. And what I mean by that is, again, if you sort of, started with this guy and then you converted it from unit A to unit B and you got an answer here, I would not round very much here. I would probably keep the whole number, just kind of think about where we should be. And then maybe you went from unit B to unit C. Those guys cancel. Again, getting another number here. I would avoid rounding. Maybe you then took that number and did one more conversion. I would wait to round to the very end. And the reason for that is if you round a lot after, say, the first conversion, and then you do the next conversion, you round a little bit more, you're basically going to be moving yourself further and further away from probably the correct answer. So it's always a good rule of thumb not to round too much until the very end. But it's perfectly fine to do sort of conversion problems in sort of multiple steps. But again, try not to round too much to the very end and kind of clear it up. Again, we may get a couple numbers where we have sort of 2 different sort of conversions that we need to do, kind of like the feet per minute that we talked about earlier. A doctor ordered a pre-prescribed dose of 0.15 milligrams. If you only have a 50 microgram tablet in stock, how many tablets should you give? So we want to kind of think about a couple of things. First off, We want a relationship between milligrams and micrograms here, which is what we have here. And we have kind of a conversion factor given to us in the problem that basically one tablet is 50 micrograms. So what we want to do is really get everybody into the same units so that everything cancels. Because they prescribe 0.15 milligrams, milligrams and micrograms are different units. So what they decided to do was to first go from milligrams to micrograms. So they use this conversion factor here to do that. And if we just stop the calculation sort of right here, milligrams and milligrams would cancel. We would be left with micrograms. And that's good because the tablets are in micrograms. And here, micrograms per tablet, the micrograms cancel, tells us we need about 3 tablets there in this particular case. In terms of significant figures, you would look at the 50, you would look at the 3 significant figures there in the 0.15. And in this particular case, actually the conversion factor that came from the problem has the smallest number of significant figures, is actually 2. Really, that probably should be 3.0 tablets to be sort of correct in terms of significant figures. But obviously you would probably want this as 3.0, technically speaking, if you're doing sort of strictly significant figures here. How many minutes are in 1.6 days? So let's talk about this, and let's talk about some conversions that will probably not be given to you. There are some pieces of information that you probably should know, and let's review a couple of those important ones. There are 60 seconds in 1 minute. There are 60 minutes in 1 hour. There are only 24 hours in 1 day. Can't tell you how many people go with the 60 here because they probably did 60, 60 and just go 60. Clearly 60, too many hours in a day. So here again, if you wanted to sort of take this, we have 1.6 days. Again, you could think of it as days up on top. We could obviously use this here, for example, and we could write 2 conversion factors. 1 day is 24 hours. Our 24 hours is 1 day. Here we want to go opposite, which means we do need the conversion factor over here. And that gives us 1 day on the bottom is 24 hours up on top. The days do cancel. Again, you could get an answer at this point if you wanted to. I wouldn't round too much, or you could just continue on with the calculation. I'm going to actually just continue on with the calculation. The units that I am left with are hours, which are on top. I want to end up with minutes, so I can use this equality to write 2 conversion factors, which is 60 minutes is 1 hour. Our 1 hour is 60 minutes. Knowing in the way I wrote it here, I could clearly see that hours are up on top. So I do know to go opposite of that there to cancel it. Gives me 1 hour on the bottom and 60 minutes up there on top. Hours will cancel. Again, math-wise here, we're taking 1.6 times 24 times 60. On my calculator, I do yield 2304. The units that are left are minutes. That's the only one left. In terms of significant figures, that is an exact number. Don't need to worry about it. That really is an exact number. Don't need to worry about it. Again, defaulting back really to our original number has 2 significant figures. Here we would probably want to take it to 2300 minutes. Questions on that one there?
How come you made it 2300 minutes again?
Yeah, so it would be has to do with the significant figures. So we basically use two conversion factors which come from those equalities, and those really are sort of English to English equalities and all those things. So technically speaking, this would be considered an exact number, so you wouldn't have to worry about it. This would be considered an exact number, which you wouldn't have to worry about it. So really the only number that we had to worry about was that original number of 1.6, and 1.6 is two significant figures. And the reason we look at that original number and we look at the significant figures is if we just think about the math that we're doing here, we're basically multiplying right across the top. And then we're coming back and dividing by the bottom. And if you remember the other day when we talked about sort of doing calculations in significant figures, when you multiply or you divide, your answer should have the same number of significant figures as the number with the least number of sig figs. So pretty much in conversion problems, when you set them up as dimensional analysis, pretty much the only sort of math operation that you're doing is multiplying and dividing. And that means that we're really looking for whichever value there has the lowest number of significant figures. And again, because the 24 hours in a day and the 60 minutes in an hour are considered exact numbers, we would default back to that 1.6 as being two significant figures. Other questions?
Yeah, I have a question.
Yeah.
So that could be applied to like metric to metric?
Yeah, so pretty much any conversion. So the correct answer is this: in terms of equalities, if you have a metric to metric equality, which gives you conversion factors, those are considered exact numbers. If you have a metric, an English to English equality that gives you two conversion factors, those are really considered exact numbers. Technically speaking, the only one that's really not considered an exact sort of number for equalities is one where you go from metric to English. So like pounds to kilograms or something like that, like we saw. Those, technically speaking, you should look at the significant figures and use that when you're making your decision. For lecture, you don't necessarily have to, because it really will probably most of the time be that original number, but technically speaking, you should look at them. So what an exact number is really something that's a definition or something that's counted. And what that basically means is it's considered to have pretty much unlimited number of significant figures. You pretty much can put as many number of significant figures you want on that particular number. And that's why we typically will ignore it when we're doing calculations that have them involved, because it could vary from person to person, depending on how many numbers that they put there. So that's why we sort of ignore those in calculations. Other questions? Okay. All right, so let's take a look here. If your pace on the treadmill is 65 meters per minute, how many minutes will it take you to walk a distance of 7.5 kilometers? Why don't you take a second here and give it a try, and then we'll talk about how to approach it. Maybe put something down that might be helpful. Excuse me. There should be 1,000 meters in a kilometer would be helpful. So why don't you give that a go, see what you come up with, and we'll talk about it here. So we got a couple of things happening in this particular one. We do have this, which is kind of meters per minute, sort of a rate, right? And what is a rate? It's kind of like a distance per time. And this is really just a distance. And we do need to use both of those to end up in time, because that's ultimately what we're looking for, right? So we're really looking for time. Now, we do have a problem here, because this distance unit in this conversion here is in meters. This guy is in kilometers. So they definitely will not cancel each other out. So we do need to get them into the same unit. So you could either convert the meters to kilometers, or you can convert the kilometers to meters. And that's what I'm going to do. So the first thing I'm going to do is take the 77.5 kilometers, and I'm going to convert that into meters so that it will be in the same unit as my sort of guy that was given to me on the problem here. That is 1 kilometer is 1,000 meters. And that will get me 7.5 times 1,000, 7,500 meters. That is good because now I could use this guy as really a conversion factor. Basically, that means 65 meters per minute, or in a minute, you go about 65 meters there. And using that as a conversion factor, we would take our 70, if I write it there, 7,500 meters. Again, we see meters are up on top, so we want to go opposite to cancel. I mean, we want to do that. That's going to also convert us from distance into time. The meters will cancel. So we're basically taking 7,500, dividing it by 65, gives us a 115.3846154 on our calculator, obviously, and the units would be minutes. Clearly, that is a lot of significant figures going on there, and you should not report all those. Let's just keep track of kind of what we did. Really, we should look at both of these numbers here because they're really specific for the problem. They're not like a known conversion factor, like, again, 12 inches is 1 foot. This guy really has 2 significant figures. Really, this guy here has 2 significant figures, which means we really should probably end up with about 2 significant figures on our answer, which means we would actually take this to about 120 minutes in this particular case if I was doing the problem here. I think I saw that float through the chat box there and some answers similar to it. Any questions on that there? So again, I really didn't do much rounding until the very end, and that's a really good sort of rule of thumb that you want to sort of hold off on that rounding to the end. You should definitely sort of keep track of where it should be. But again, on most calculations I do, and it's probably a pretty good way of doing it as well, is I just kind of take the whole number in the calculator and continue on with the calculation rather than doing a lot of extreme rounding. Sometimes if you do want to sort of round the number, for example, let's just say we had a number like, 3.2246589 or something like that, and you wanted to round it to maybe continue on with the calculation, and maybe you technically significant figure wise should end up there. I personally would probably keep, a few extra digits, maybe to the 4, maybe to the 6, and then continue on with the calculation. And then at the very end, kind of clean it up there to 2 significant figures when it's all said and done. The question is sort of which one would be acceptable for the exam. Technically speaking, the correct answer here should be 120 minutes. It's the correct answer, which has 2 significant figures. Other questions on that? Now, clearly, if you put, like I saw in the chat box there, maybe like 115 and some of those other ones, there's kind of, I guess the way to put this is there's correct in terms of doing the calculation, right? And sort of doing the calculation correctly and getting the number on your calculator. But we also want to make sure that we are correct in addition to doing that, correct in the way that we report the answer to the correct number of significant figures. So almost like a 2-part approach to the answer, doing sort of the calculation part correctly, but also reporting it correctly in terms of what the answer should be in terms of the significant figures. 120 written like that would have only 2 significant figures because remember here that 0 at the end would not be significant because there's no decimal point in the number. If you wrote 120 and put a decimal point there, then that one then becomes significant and would have 3 significant figures. But without any decimal point written in the number anywhere, all the zeros that come at the end, again, are not considered significant. And to answer the other question, yes, you could absolutely write it in scientific notation is perfectly fine. If you wrote like you did there 1.2, times 10 to the 2 would be perfectly fine, obviously, with the units. What would be incorrect, right? If you wrote kind of this would be incorrect because now this would have 3 significant figures, right? So as we talked about earlier, when you do write in scientific notation, all the numbers before the times 10 part are significant. So as you typed in there, and as I wrote it first on the screen with the 1.2, that would maintain the correct number of significant figures that our answer should have. Other questions? All right, so why don't you try one here? You go to the local AM PM, you got 32 fluid ounce drink of Diet Coke. How many gallons did you drink? Let me give you some equalities that might be helpful for you. There you go. And I'll even give you the conversion factors there as well. All right, so see what you come up with here. How many gallons of Diet Coke did you drink? Okay, let's take a look at this one here. So we are starting with 32 fluid ounces. We want to roll to gallons there. And so we got a couple of equalities to do that. And obviously our conversion factors here that we could write for each of these guys. We would want to start with our 32 fluid ounces. We want to get rid of fluid ounces, so fluid ounces are on top. So we can use the conversion factor there where it's on the bottom. And again, if I stop the calculation right at this point, fluid ounces divided by fluid ounces would cancel. I would actually be left in the units of quarts, which would be on top. That's close to what I want, but again, do want gallons. So we do want to go one more sort of conversion. I'm going to continue on with the calculation. You could get an answer and then can continue on. But here I do see by writing it dimensional analysis way, my quarts are on top, which tells me to fix that. I need to get rid of the quarts by putting it on the bottom. That would be my conversion factor there on the right. Our quarts now will be divided out, leaving us just gallons that are left on top, which is good. Here we're going to take 32 times 1 hit equals. Divided by 32, I would hit equals. Divided by 4 and then hit equals. And you do end up with 0.25 gallons as your answer. You do not end up with 1 divided by 4. That's because that makes me think you're too lazy to divide it. So typically speaking, you should not leave an answer here in chemistry as a fraction. Maybe not so bad in this example, but I have seen people write something like 325 miles divided by 1,280 hours. That looks like a great answer and not divided. So don't leave it as a fraction, divide it out. In terms of significant figures here, really exact number leaves us 2 significant figures we started with, 2 significant figures that we ended with. I saw some of those answers in the chat box, so that looked good. Any questions on this particular example here? Should agree with me. Good. All right, let's try another one here. A patient receives 5 pints of plasma. How many milliliters of plasma were given? So give that a go here. Let me give you some info that might be helpful here. Here are some equalities and see what you come up with here. Okay, let's take a look here and sort of see how we're doing. So we got 5 pints. We basically want to go from pints to milliliters. We got some equalities and then obviously our conversion factors here that we could get from those 2 equalities. We're going to start with our 5 pints. Again, pints are on top. So we do want to get rid of it. We're going to go opposite, which would be here first. 2 pints on the bottom is 1 quart. At this point, pints divided by pints cancel. We have quarts there on top. We do want to get to milliliters. So to get rid of the quarts, we will go opposite and use the conversion factor on the right there. putting our quarts on the bottom, our milliliters up on top. Again, quarts divided by quarts will cancel. Math-wise here, we're going to take 5 times 1 times 946, hit equals, divided by 2, hit equals. And on our calculator, we end up with 2365 milliliters. We do want to look at Sig Figs here again, pretty much exact number, which means you don't have to worry about it. Defaulting back to sort of, as I mentioned earlier, our first number, 2 Sig Figs takes us to here. Means we do need to round up in this case. So 2400 milliliters. Or again, you could do the scientific notation route to the 3 milliliters there. Any questions on that answer or calculation? All right, let's try another one here. You're 125 miles away from home with no money. You decide to walk it. If you walk 55 feet per minute, how many days will it take you to get home here? So give you some things there. All right, take a minute or two to see how many days I'm walking for. Probably a lot, I imagine. Okay, let's see how we're progressing here. So again, we got a couple of things given to us. We got our miles, our distance, and again, we have sort of that rate, kind of like what we were talking about earlier. We have kind of a similar situation here. The sort of distance here is miles, our length is miles, and that is feet. These are 2 different units. So we do need to do a conversion to get them into the same unit. This guy here, which is our rate, is going to allow us to go from really distance to time, which is what we're looking for since we're trying to find how many days. So again, you can do the feet to the miles or the miles to the feet. I'm going to convert the miles into feet to begin with. So I'll start with the 125 miles using my equality here. Opposite would be putting my mile on the bottom. 5,280 feet on top. The miles will cancel each other out. And that yields me 125 times 5,280. Looks like 660,000 feet. Now that I have that in feet, I can now use my sort of rate as a conversion factor. I could use it like it's written as feet per minute. I could also flip it around and put minutes on top and 55 feet on the bottom. And that is how I'm going to actually use it like that so that I could cancel out the feet. This would be 55 feet per minute. Feet here will cancel. That will now convert me into minutes, which is close to what I want. I'm now in a unit of time. But I don't really want minutes. I do want days. So again, there's multiple ways you could kind of get there somehow, but I do know that there are 60 minutes in 1 hour. Again, the minutes will cancel each other out. If I stop right here, I am in units of hours, which is close to what I want, but I do need to go from hours to days here. I do see hours up on top. So we will put hours on the bottom, which is 24 hours and 1 day. Hours will cancel. We're going to basically multiply across there. So that's basically 660,000 times 1 times 1 times 1. Don't really need to put that in, but you can if you want. Hit equals. Now here again is a situation where people will sometimes get the wrong answer because they want to put everything on the bottom in their calculator all at once. And if you don't do parentheses correctly and stuff like that, you will get the wrong answer. So personally, I would do this by taking my answer I got on top, dividing it by the first number, which is 55, hit equals, divided by the second number, which is 60, hit equals, divided by the third number, which is 24, and hit equals. And you will end up with 8.33333, a bunch of threes, days. So let's talk a little bit about significant figures. Really, you know, there's two numbers we should look at here. Whereas the first number that was given to us, which is 3 significant figures, and I didn't change it on this particular handout I'm looking at. I don't know if I changed it on your handout or not, the actual handout, but sometimes I have 55.0. But the way it is here, it is 55 with no 0.0. That is 2 significant figures, which means really this probably should end up at 2 significant figures, which means probably like an 8.3 days. And I say that because I don't know if on the handout I put up on Canvas, if I did change that to 55.0. Sometimes I did in the past, I can't remember. But if it does say 55 like that, 2. If it says 55.0, then it should be 3 significant figures. But I think it might still say 55 on your handout. Any questions on that particular calculation there? All right. Any questions on conversion factors, equalities, or anything like that? So we're going to then talk about density. Density is basically decides, for example, in water, if something will sink or float. If something is more dense than water, it will sink. If something is less dense than water, it will float. Water, for the most part, has a density of 1 gram per milliliter. Should note that density does change with temperature. So if we're talking about different temperatures, you'll sometimes have a different density value for something like water. But probably 9 times out of 10, somebody asks you, what is the density of water? They're probably talking about the 1 gram per milliliter. Water is an unusual substance. Most substances are more dense in their solid state than in their liquid state. But as we can see here, ice, which is the solid state of water, it's actually less dense than liquid water, which is why our ice cubes float in our drinks. And that's just an unusual property of water. Density really is the mass of a substance divided by its volume. It is D is equal to M over V. Common units are grams per milliliter, are grams per cubic centimeter. And that's usually for solids or liquids, which is mostly what we come across in this class. Sometimes the density is given in grams per liter for gases. We don't come across too much of that, but sometimes it does occur here. How do we get a cubic centimeter? Remember, if you take the length times the width times the height of an object, and they're each measured in centimeters, that gives you a cubic centimeter. Also good to note that 1 milliliter is the same as 1 cubic centimeter, or 1 cc, as we also saw. Now, this is an equation where you do need to solve for any of these 3 things. So D is equal to M over V. Volume would equal mass divided by density times volume to both sides, divide by density. Mass is equal to volume times the density. Sometimes people like to remember this by the DMV triangle. DMV. Density is mass divided by volume. Volume is mass divided by density. Mass is density times volume. So it's a good way that you could kind of figure it out there. So substances that have higher densities contain molecules that are typically packed very close to one another. Again, lower densities means they're a little further apart. And that's actually what happens with ice when water comes together in ice. What ends up happening is you get all this really empty space between different water molecules. And if you think about what density is, mass divided by volume, all that empty space increases the volume part of the calculation, which means smaller number up on top divided by larger number gives me a smaller density value. And again, that's why we see a sort of smaller value for density in terms of something like ice. As I mentioned before, these are the typical units that we associate with density. They both are there at the end. the number typically always stays with the grams part, and it's like per 1 milliliter or per 1 cubic centimeter. Here's again a table of some common density. So here's our water in the middle. Everybody sort of above it here would sink. Really, everybody below it would float. If you have solutions of different densities and you put it into a test tube, they would separate out into different layers based on their density. The most dense layer would be on the bottom. The least dense layer would be on top. And if you had something you threw in there and it just kind of floats there, like the previous picture we saw, that would mean that this guy here is more dense than what's above it. It is less dense than what is below it, basically. Kind of almost suspended there. Let's get that real quick here. Let's talk a little bit about a very common way that we get a volume when we're doing density. There's really 3 common ways to get a volume. You could actually just do a reading. So just take a volume reading. You could actually do the length times the width times the height. Or the more common way is volume by displacement. And basically volume by displacement means we take a volume of a liquid, we take a solid object, we drop it in there. And when that object goes in there, what's going to happen is the volume level is going to rise. And the solid object will basically displace a volume that's equal to its own volume. So if we basically take the difference there, I missed the line, we'll just create it that way. The difference between our initial volume and our final volume, that will give us the volume of the object. The volume of the object would be the final volume minus the initial volume. And that again is a very common way to calculate the volume in a density problem. So for example, here they took a piece of zinc that had a mass of 6.860. They weighed it. They took an initial volume reading here of their graduated cylinder, which was 35.5 milliliters. They took the zinc and they dumped it in. The volume went up to 45 milliliters. We subtracted here to get the volume of the object, which was 9.5. We then divided the mass by the volume, gave us a density of 7.2 grams per milliliter. Significant figure wise, 4 significant figures on top. When we subtract here, we go to decimal places, which gave us 2 significant figures. Our answer ended with 2 significant figures. Question on that there. Okay, so I think what we'll do is we will lay it up there. We're pretty much almost done with this chapter, just a little